Okay, good afternoon, everyone. My name is Jade Moore, and I go to Jackson State University. I am a physics major, and today I'm going to be explaining my research. The title is Radio Frequency Astronomy and Submillimeter Instrumentation. So here is a quick look at what I'm going to be talking about today. My projects were theory and instrumentation. So I'm going to talk a little bit about both of them. I'm going to introduce some TNOs, some calculations and plots that I did, as well as talking about a proposal that we submitted a few days ago for Planet 9 research, as well as the LATR, which I will explain in a little bit. So starting off with TransNeptunian objects, I'm going to refer to them as TNOs. TransNeptunian objects are objects that orbit out past Neptune. So their semi-major axis is above 30 astronomical units. And these are fairly small objects. So they're smaller than the average planet. Of course, a TNO, a very popular TNO would be Pluto. That's on the larger ends of things. But with them being so small and them being so far away, they're very, very hard to look at, especially with optical telescopes. So they're usually looked at in other ways. Here we have two graphs showing a distribution of their orbital size, the semi-major axis right here on the left, as well as their average diameter, which is on the right. So some contributions that I made to this research. Initially, the TNOs that I was looking at were going to be used for calibrations in our Planet 9 discovery to be, hopefully. But we decided to make them two separate proposals and save the TNO one for the future. So here we can see two separate graphs of TNO positions. And I started out with a database or a few databases of TNOs. And I was given the responsibility to compile them, cross-reference them, and find important information like size and distance and brightness based on those multiple databases that I was given. So once I found that, I was able to make a cut based on the telescope that we wanted to use, which is the Green Bank Telescope in West Virginia, and the Mustang receiver, to be specific about which receiver that we wanted to use. So we made cuts based on the declination of a -15, and you can see that the before is at the bottom, and then when we made the cuts is at the top. So based on these cuts, we were able to go on and look at the visibility plots. So the black bar in the center is what the Mustang receiver can see at any given time, and that green arch is the actual TNO's placement in the sky throughout a certain amount of time. So here we can also see a different plot of TNOs or TNOs that made the cuts specifically. The size of the individual dot is relative to the diameter of the TNO, and then the color is representative of the temperature of the TNO. So the hotter, the brighter, the easier it is to see, the larger, the easier it is to see. Speaking of TNOs, a reason that we have decided to study them is because of Planet 9 and how they interact with each other. So Planet 9 is a hypothetical, a placeholder name that we have given some object that is out somewhere in the solar system. So the reason that we think Planet 9 exists is because of a paper that Konstantin Batygin wrote about 5 or so years ago, introducing the idea that there's a new planet out there that's interacting with these TNOs and causing these strange abnormalities to happen that can't be explained by the orbit of Neptune. So he proposed that Planet 9 is some object 5 to 10 times the mass of Earth and roughly 400 to 800 astronomical units away from the sun. So what evidence have we found of Planet 9? So there are two main abnormalities that we have noticed in the solar system. First, we have Sedna as a perfect example, and I'm going to try to make this easy to understand. So this is a top view of our solar system. The orbits that you see here are TNOs. They're not the planets, they're TNOs. So in the very, very center is the sun. And we can see that the closest portion of each individual TNO's orbit is clustered on the right side. We can all see that. With regular distribution, we would expect it to look like the petals of a flower. You know, it would be regularly distributed around the sun, but we can see that they're all kind of hanging towards the bottom half of the solar system. This leads us to believe that there's something interacting with them gravitationally. There's something pulling them towards one side that we can explain. And we've looked at the models that we have of our solar system, and nothing really explains that, not even the orbit of Neptune. Another abnormality that we have noticed is a side view of the solar system. So if we were to draw a line through this plot, that would be the horizontal axis of the solar system. And we can see that the TNOs orbits, none of them fall on that perfect horizontal axis. No one's perfectly going around. We have some that are angled up, we have some that are angled down, and no model of our solar system can explain why these TNOs are doing this. So that's why we need some other explanation, and we think it is another planet. So in a paper called the Atacama Cosmology Telescope, A Search for Planet 9, people actually thought that they had enough to look for it, and they came up with these 10 candidates as possibilities for Planet 9. So with these 10 candidates, we proposed to search for Planet 9 using the Green Bank Telescope and the Mustang receiver. So our proposal went out on August 1st, and it was basically to use the Green Bank Telescope to observe 9 of the 10 candidates that we found in the ACT paper. So using these 10 candidates, we were able to group them together based on where they're located in the sky between our observation window, which is January of next year, until April of next year. So here we have a plot, and you can see perfectly that based on our expectations of the data that we want to receive, individual factors put in place for Planet 9. So remember I gave you a range like 5 to 10 times the mass of Earth. These are based on the individual factors given by the parameters. So each individual line is a possibility. And this is the data that we would like to receive when looking at them with the Green Bank Telescope. So the signal expected, we have an antenna temperature plot as well as a flux density plot, and both of those are very important when it comes to looking for Planet 9. So outlooks and forward plans. The outlook is of course, if we're able to find another planet, that would be absolutely amazing. It's been almost 100 years since we've discovered a new planet in our solar system, and I definitely believe that there is one out there. If we are observed for this time at the Green Bank Telescope, it would be great motivation to continue to look. Any sort of evidence that we get, or even evidence that it isn't in a certain place, is great motivation to continue to look with even more sensitive telescopes. And the reason that we actually chose the Green Bank Telescope and the Mustang receiver is because of its sensitivity. It's a promising way to search for Planet 9 because it's so far away and we can't look at it with an optical telescope. So speaking of other telescopes to use, the second half of my presentation was with the Simons Observatory and the LATR. So speaking of the Simons Observatory, they have 2 main projects, which is the Large Aperture Telescope, as well as 3 small aperture telescopes, which Tana had just explained. So working on the Large Aperture Telescope receiver at the University of Penn, I have been really just digging in deep, learning how it works, learning the mechanics behind it, and trying to get a great understanding of the CMB. So the LATR is what I'm going to refer to it as, is the instrument that will actually be doing the surveying of the sky within the telescope. So it's looking at millimeter wavelengths. So it's not an optical telescope. It's looking at radio waves and things of the sort. And it would be a great way to search for Planet 9 once it's up and running. So this will be in Chile, like Tana said, and we're hoping to deploy it next year and be up and running by 2023. So this is a picture of the bottom of the LATR, which you can see the lensing as well as some filters. So as far as my contributions to the LATR, I was a part of installation of filters on the 40K and 80K stages. There are 5 stages to the cryostat, which is the entire casing, and within the cryostat, there are 7 optics tubes. So the cooling goes from room temperature, which is 300 Kelvin, all the way down to 100 millikelvin within those 5 stages, and there needs to be filters in each individual stage. So I was a part of that, which was really cool. I also did some readout testing. So our most recent cool down didn't go as expected. We reached the 100 millikelvin stage, but it didn't get as low as it did in the past. So some of the readout testings, like the low noise amplifier test, were able to help us figure out why it wasn't doing what we thought it would do. So the low noise amplifier test basically um, caused vibrations or heat within those really, really cold stages to see how they were interacting with each other. So if we cause heat in one stage, and we see heat increase in another stage, we know that there's some sort of connection between those two that shouldn't be there. And we can move forward with fixing it or changing it and making it correct. The second test that we did was the loopback test, and that basically was able to check the cables used throughout the cryostat to transfer data and things of the sort. So throughout the summer, this is what I was working on at UPenn. These are my references and the papers that I referred to throughout this presentation, and some acknowledgments that I would like to make. My wonderful, wonderful, wonderful mentors, Casey, as well as Professor Mark, for allowing me to be a part of his project. Are there any questions? Yes, to the question in the back.
Yeah, thanks. You said you think something's heating up due to vibrations.
Right.
What do you think is vibrating? Have you guys found?
So actually, when I meant vibrations, that was a part of the testing that we used. So we actually used vibrations to heat up something in one area and see if there was any temperature changes in another area. So we were causing the vibrations. Oh. That's what I meant when I said that. Does that make sense? Okay. Yes, right.
So I was wondering, do you happen to know of anybody who argues against the existence of Planet Nine and what kind of cases they make? Like, what is their evidence? It seems like there's very strong evidence for it.
That is actually a really good question. I'm not sure about anyone who argues against the existence of Planet Nine, but I know there are a lot of other thoughts. Some people think, I've heard black hole, I've heard a lot of other things other than a planet. So Planet Nine is just a nickname that we've given it. We don't actually know that it's a planet.
Oh, I see. Thank you.
Yes.
I was going to say, I argue against it.
You do?
What I mean by that is, it doesn't exist till we observe it to exist.
Would you mind using your seat mic?
Yeah, that the TNOs are actually evenly distributed, but our observations are biased towards a portion of the sky, but they haven't been able to disprove the existence of Planet Nine, so it's not conclusive yet.
Are there any more? Yes, Kayla.
So, what exactly about this data, I feel like, leans people towards Planet 9 in general? Because, like, when I looked at that map, I was thinking, okay, so how do we know these aren't just captured objects, right? They didn't form with the solar system because they're not in the right plane. But how do we know they're just not captured? And then, like she said, if the data is biased towards one direction of the sky, they could just be stuff moving in all different directions, or orbiting rather.
I think that would be a wonderful case for the high inclinations, which is on the horizontal plane. That's a great case that it could just be random captures of these objects that are out in space. But as far as the high, I would say, which was the first, I can go back. So in this case, I wouldn't say that's random. If it were random, like I said, it would look more like evenly distributed throughout. So the fact that it's all in that one general area on the right side, I feel like there has to be something interacting with it that we just don't know about yet, whether that be a planet or whether it be something completely different. There's some sort of interaction going on there that we can't account for. So that's why people lead to think that there's some object out there on the other far end, kind of attracting it towards one specific direction. That makes sense.
Maybe we can do one more question and then we should move on.
Okay. Yes.
Okay, so for Planet 9 candidates, you guys actually had like legitimate radius and temperature estimates for what you would expect the planet to be.
Right.
How did you get those values? Are they like according to like what you would assume the gravitational attraction of an outside Planet 9 would have on the solar system, or from those?
These 10 candidates were actually chosen in that Atacama paper. So those people were the original creators of those 10 candidates. They got those ideas. Now I can tell you a little bit more about the methodology that they used, called the stack shift method, where they were basically able to find these individual candidates. But as far as the parameters and of that sort, I would have to get back to you on that.
Okay, thank you.
Okay. So I will just say one of last year's scholars actually detected another planet in another galaxy. I never thought that this year's scholars would top it and find a new planet in our own galaxy. So let's thank Gabe one more time.